Okay, welcome to Exponential Growth and Decay. So, back a little while ago, we were talking about compound interest and if it was compounded continuously, we had the equation A is equal to PE raised to the RT. Okay, so in growth and decay, they like to use A is equal to A naught, all right, E to the KT, all right. Everything still stands the same. So K is still your rate, and this is your decimal form. Okay, now here is the key. If K is positive, then it is growth. If K is negative, that means it's a decay. And I spelled decal instead of decay. So let me fix that now before I forget and have to do the video all over again. All right, so there's K. So what is a naught? A naught just means initial. It could be population, it could be amount, whatever, okay? And A is your final, all right? So initial could be the population in 1940, and A, the final, could be, hey, what's the population in 2021, all right? So that's kind of like what it is there. And T is, of course, your time in years. All right. So I just want to do a couple of examples here just so that you guys have those particular ones. All right. And here we go. I kind of want to do ones that I think that you will need the help to do. I think if everything is kind of, placed, the A naught, the E, the K, the T is all right there, then you just plug in your calculator and you're done. The question is, what if they're asking for what the K is or what the T is, and that's in the exponent, then what do you do, okay? So for example, they were talking about where, the initial, so let's see, I mean, it's kind of sad to say it. Let's say that an illness came about, and what happened was that we started off at 51.2 million people, okay? And we ended with, 36.4 million people, right? And this is occurring in 14 years. All right. So question is, what is my K? All right. So if you look at this, if my initial, and I'm starting off with 51.2 and I'm ending with 36.4, so it's going down. So therefore, I must have a decay. Okay, so decay can happen with population as well. So when I put this into the equation, I'm going to have 36.4 is equal to 51.2 times E raised to the K times 14. So let me write this better here in terms of what is more pleasing to the eyes, E to the 14K. Okay, so question is, how do we go about doing this? So first thing I'm going to do is I want to get the E by itself. Actually, I'm going to write this E a little better here. E, there we go. That looks way better. All right, so first thing I want to do is get the E by itself. So in order to do that, I have to divide by 51.2. So what I have is, let me see what 36 divided by 51.2 is. So 36.4 divided by 51.2, So I'm getting a 0.71 dot dot dot. And I'm going to leave that on the calculator. Is equal to e raised to the 14k. Okay, so your question is, well, how do I go from there? All right, so what I'm going to do, because it's e, I have to use the natural log. So I got to do the ln of this 0.71 dot 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 is equal to the ln of e raised to the 14k. All right, so if you notice the right side, these two here are my opposite operations. Okay, so therefore they cancel each other out. So the right side is just going to be 14k, where the left side is going to stay as my ln of this number that I still have on the calculator. Okay, so now from there, to get k by itself, I just got to divide by 14. Okay, so that means my k is going to equal to, so right here on the calculator, I could just go, okay, I'm going to take the ln of the answer, which is second negative sign, hit enter, and then hit divide by 14, hit enter again, and I'm going to get a k. You know what, I'm not going to use the equal sign, I'm going to use the approximate sign. And that's going to be negative 0.024. Okay, so there's my k. All right, so again, I already predicted that because my initial was higher than my final, that means my final is less, so therefore there's some decay, so therefore my k would have to be negative. Okay, and if this was flip-flopped, if the initial was 36.4 and the final was 51.2, then there's a growth, right? And then if there's a growth, then my k will actually become positive, all right? So you got that growth and decay, and then something that you also learned in science is called half-lives, okay? So with half-life, so if I had the formula here of growth and decay, e to the kt, all right, so what happens with half-life? If my initial starts off with an unknown amount, okay, like a naught, all right, what would be my final amount? Keep on putting that naught in there. So what would be my final, right? So let's take a look. If I started off with my initial to be 10, then my final would be 5 because it would be half, right? If I start with 50, then my final would be 25. Does that make sense? And I can just keep on going with these examples, okay? So in other words, whatever I start with initially, right, then my final amount is gonna be a half of the initial amount. Everybody understand that? So my initial amount is a naught. If it was 10, then at the end, my final amount is gonna be just half of that. So if I put this back into the original equation here, that means my final amount is always gonna be half of my initial amount, is equal to the initial amount, e raised to the kt. Okay? If I was to divide both sides by a naught, what do I have? I have 1/2 is equal to e raised to the kt. Okay? So, let's see if I can find a half-life problem here for you guys. Okay. That's a decay. Okay. go. So it's saying that this is giving an example. Let me see. That was just, I'll put down example 1 here. And I'll call this example 2. Okay, for Half-Life. So this is telling me, so the problem is just telling me, hey, decay is equal to negative 0.097, okay? And it wants to know what the year is, what the, how long it takes for half the product to be left over, all right? So when you initially read this problem, you kind of freak out because you're like, well, what was initial? What was my final? But if you notice, what happens is that because my final amount is going to be half of my initial amount, my A naught, my initial amount kind of goes away. So now I'm left with just this formula here, which is very different. So I'm going to actually show you using the original formula up here, okay, this original formula here. So I'm going to say, okay, I know that the final amount is equal to initial amount times e to the kt, okay. I know that no matter what the initial amount is, my final amount is going to be half of a naught e to the negative 0.097 t, okay? So I know that. So I still do the problem the same way, divide by a naught. So now I have 1/2 is equal to e raised to the negative 0.097 t. So notice that I started with the same exact formula no matter which problem I'm doing, okay? So that this way I don't have to try to remember this special formula here for Half-Life. All right, I just have to remember and think about, okay, with Half-Life, my final amount is just half the initial amount, okay? So again, I'm kind of getting stuck where I have the t in the exponent. And because the base is e, I do have to take the natural log of 1/2 is equal to, oh shoot, I wanted that to be that. And then the ln of e to the negative 0.097 t. All right. So now I have, so I'm going to go on to the calculator. When I take the natural log of 1/2, I'm going to have negative 0.69 ... is equal to negative 0.097 t. So don't forget, opposite operation. Okay? So they kind of cancel each other out. So then I can just divide by negative 0.097. All right. So therefore my time is going to be, let me see, take that divided by negative 0.097. So it's going to be, do approximate again, approximately 7 years. Okay, so therefore there is my answer. Or actually, better yet, let's do it this way, is approximately 7.1 years. Okay, because I believe the direction does say round to 1 decimal place. Okay, so those are only 2 examples I wanted to show you coming to exponential growth and decay. And guys, if you have any questions, you know